Hello everyone, good morning. This is Mr. DHAKSHUNHAAMOORTHY, Assistant Professor, AIML Department. Today's topic is multi-agent RL. In Unit 5, Deep Reinforcement Learning, Multi-Agent Reinforcement Learning, MARL. The form of reinforcement learning RL, agents learn to take actions that maximize a reward derived from the environment. Multi-independent actors or agents, each agent's action may change the environment, and changes to the environment could affect the reward for all agents. Agents may interact to maximize the reward. Intentional changes to the environment, direct agent to agent communication, cooperation versus competition. Markov decision process MDP. The typical RL problem characterized by a Markov decision process MDP is the following parameters. S is set of possible states in the environment. A is set of possible actions. The agent can take a reward function R. P is the state to state transition and probability based on action. In general, agent will take an action AT on the environment, then the environment will get transitioned from ST to new state ST plus 1 and produces a reward RT plus 1. So these two will be fed back to the agent. If the reward is in a progressive manner, then the agent produces the current action as it is to the environment, or else the agent will correct itself and giving the action which gives the maximized reward. Stochastic games, the combination of Markov decision process with a repeated game. Here the agents must account for and actions of other agents. These two combination we have to see. And stochastic game parameters, n number of agents. AI is the action set for the agent I, and A is the combined action. In combined action, A1 cross A2 dot 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 AN, where R a reward function for a combined action A. See, in the multi-agent RL, the previous diagram we seen about one agent will take an action on the environment. Here there are multiple agents, agent 1, 2, dot 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 AI. There are n number of agents available in this multi-agent environment, where the combined action of all the agents is cumulatively sending to the environment. And then based on the action taken on the environment, we are getting the states and reward from the environment is fed back to the all the group of agents. MARL challenges. Moving target. A reward for each agent can be affected by actions of other agents. Agents action change over time. Action reaction loops can cause rewards to fluctuate. And the reward distribution. which action from which agents lead to states with large rewards. Impossible to maximize each agent independently. Curse of dimensionality. More agents can increase observation and action spaces, and complexity grows exponentially with the space and state dimensions. Multi-agent grid world. A square grid world of size S is greater than or equal to 6. Suppose n agents, n is the element of 2, 3, 4. The process n actions per time step. Return n unique rewards. So we can see action space, observation space, agent communication, all three in the diagram. Observation space. Next, the current agent position, row comma column, that we can depict in the picture, and action space, 5 possible actions: move up, right, down, left, don't move. There are 5 possible actions are there. Enable agent to agent communication. Agents should should be able to share their location with other agents. Agents. Compare the performance of two types of agents. One is tabular queue learning, another one is deep queue networks. Agent inputs: observation, current location; communication, n-1 other agent locations. Agent output: next action. For size S with n agents and a actions, queue table size equal to S square into n square into a. DQ1 input layer of size 2n. 2 dense relieve is the activation layers of size 48. Training. All agents trained for 1000 epochs. Gamma is equal to 0.95 and alpha is 0.05. Exponential epsilon decay. Epsilon naught equal to 1.0, epsilon min 0.03, and delta equal to 0.005. At each iteration, we recorded the score and land movements for each agent. The score equal to total cumulative reward for one effort. Learned movements recorded with epsilon equal to 0, greedy. Here in the plot, they just depicted the episode and epsilon value variations. Here in the earlier episodes, we are having epsilon value is 1. Once we started doing this experimentation, the episodes keep on increased, then the epsilon value is going very low value. Results shown in this slide. Here results for n is equal to 2. The plots for score with averaging over a sliding window of size 10. Here final learned path. Here agent shown in the yellow and green. Enemy shown in the blue colored. Both TQ and DQN, table queue learning and deep queue learning queue network agents, converge to the same optimal path. DQ1 agents learn much more quickly, but with slightly more noise.